Okay, today we are going to be solving trig equations. So over on the left, I've got some little pointers, tips for you guys. The main goal is we're trying to isolate the trig function. So that means we want to get the trig function all on one side, and we want to get the x all by itself. In order to do that, in order to get the x all by itself, we're going to have to take the inverse trig function. Keep that in mind. So our answers are going to be angles. Anytime we're doing an inverse trig function, our answers will be angles. The other thing I wanted to point out is number 2. It says never divide by a trig function. You'll lose answers if you do. Imagine if I had like a cosine x equals sine x, for example. And let's say I divide by sine x. Then I'm essentially saying that sine can never be 0 because we can't have a denominator equal to 0. And that's not necessarily true. Sine can equal 0. So don't ever divide by a trig function. You're going to lose answers if you do. So if you're ever checking your answers and you have like 1 or 2 less answers than the key, it's probably because you divided by a trig function. Okay, so we're going to start with this first example over here. Now we've got sine x on both sides of the equation, so I would recommend getting them together on one side. So I'm going to add sine x to both sides. So then over here I will have 2 sine x's plus square root of 2 equals 0. Now my goal is to try to get the x all by itself. So I'm going to subtract the square root of 2. So now I will have 2 sine x equals negative square root of 2. I can divide by 2 because I was multiplying sine by 2. So that means that sine x is going to equal negative square root of 2 over 2. Now to get the x alone, we're going to do the inverse sine of negative square root of 2 over 2. Okay, so now is the point where we have to think of the angles, because our answer is going to be angles. Where do you get a negative square root of 2 over 2 for sine? So sine is negative in the 3rd and 4th quadrants, and I know that square root of 2 over 2 happens like right in the middle there at the pi over 4s. So like this right here would be pi over 4, but we don't want that one. This would be 3 pi over 4, 4 pi over 4, so this is 5 pi over 4, 6 pi over 4, so this would be 7 pi over 4. I think I was pointing and realized that you can't see where I was pointing. Sorry. So our answers are 5 pi over 4 and 7 pi over 4. Okay, let's do the next one. Alright, so again, we're trying to get the x all by itself. So probably naturally what you would want to do is add 2 to both sides. So we have secant x equals 2. Now I could do the inverse secant, but I'm thinking most people are not as familiar with that in terms of angles on their unit circle. So what you might want to do is consider doing the reciprocal function, which would be cosine, and then flipping the 2 and making it a 1/2. That way it's just a little bit easier to think of the inverse cosine of 1/2. So now we got to think, okay, what angles do we get a 1/2 in the cosine spot? and this is a positive cosine, so that means we're going to be in the first and the fourth quadrant. So cosine is 1/2 at pi over 3, and then also down here. So you have to figure out what is this. So as you go around, you will get 5 pi over 3. So our answers for x are pi over 3 and 5 pi over 3. Okay. Next one. When I look at this problem, I notice I've got two terms, and that both of the terms have a cosine x. So what you might want to consider doing is factoring. There's going to be a lot of problems where factoring will be a good idea. In this case, we can factor out that common term of cosine x, and then we'll be left with 2 sine x minus 1 equals 0. Now when you factor and it's set equal to 0, we can set each of the factors equal to 0 and solve. So here, if I want to get the x alone, I will do the inverse cosine of 0, and then I have to think about where do I get a 0 in the cosine spot. So up here is the point 0, 1, and down here is the point 0, -1. Both of those are where you have a 0 in the cosine spot. So that happens at pi over 2 and at 3 pi over 2. So there's two of our solutions, but there's going to be more because I have to solve over here as well. So here I'm going to add 1, and I'll get 2 sine x equals 1, and then I can divide by 2. So sine x will equal 1/2, and then I will take the inverse sine of 1/2, and now I need to think, where do I get a 1/2 in the sine spot? And this is positive sine, so we're going to be in the first and second quadrants, and we get a 1/2 in the sine spot at pi over 6, and over here at 5 pi over 6. So we have 4 solutions, those two and these two. Okay. Next one. With this problem, what I've found is a lot of students are really tempted to divide by tangent. They want to divide by tangent on both sides. But do you remember what I had said earlier? So let me scroll back, see if this works to scroll back. At the very beginning, I said never, here we go, never divide by a trig function. So I would not divide by tangent. So let me erase that. Because essentially what you're saying, you would be saying tangent of x is not allowed to be 0 if you divide. And that's just not a true statement. So don't divide. Okay, all right. So what can we do instead of dividing? We can subtract it over to the other side. So we will have 3 tangent to the third x minus tangent x equals 0. And now it's similar to the last problem where we can factor out that common factor of tangent x. And when we do that, we'll be left with 3 tangent squared x minus 1. And now that we factored it and it's set equal to 0, we can set each factor equal to 0 and solve. Alright, so this first one, we are looking for what angles would you get a 0 for tangent. I think what you might want to remember is that if tangent of x is equal to 0, that's the same thing as sine over cosine equals 0. And if we have a fraction and it equals 0, that means the top has to be the 0. So what that means is that we're looking for where sine is 0. So where does that happen? Right here is where sine is 0, and also right here is where sine is 0. So that happens at 0, and it happens at pi. So our solutions for the inverse tangent of 0 would be 0 and pi. And then we have to continue solving over here. So I can add 1 to both sides. I can divide by 3. So I have tangent squared x equals 1/3. Now here's the thing, we haven't encountered a squared trig function, but it still behaves the same way if I'm trying to get the x alone. I can make this a tangent x if I take the square root of the other side. Just remember though, plus or minus. That right there is where people are going to make mistakes. And probably what I would do is simplify this. So that would be the same thing as square root of 1 over square root of 3. And I can then say square root of 1 is 1. Square root of 3, though, we need to rationalize that denominator. So it would be square root of 3 over 3. And to get x alone, we're going to have to do the inverse tangent of positive and negative square root of 3 over 3. Okay, now, where do you get square root of 3 over 3 for tangent? That happens at pi over 6. We would get a negative square root of 3 over 3 over here at 5 pi over 6. Here would be a positive, again, square root of 3 over 3, so that happens at 7 pi over 6. And then here we would get a negative square root of 3 over 3, and that is 11 pi over 6. So these solutions over here are pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. So we had 4 solutions here, and we had these 2 up there. So we have a total of 6 solutions for this problem. Now I just wanted to show you real quick what the back of the book is going to do. They do this really weird thing where they only give a few solutions and then they add on like an n pi or a 2n pi. Don't do that. You don't need to worry about how the back of the book does it. Just do it the way that I'm showing you. But just so you know, when you check your answers in the back of the book, you're going to see weird things like that. Okay. There's also going to be some problems where they're going to want you to graph, and they should be easy problems, except if you don't know how to type it in your calculator, then you're going to have a little bit of issues. So, for example, if this is what I want to graph, y equals sine squared x minus 1/2, there's no way to type it in where you get the squared. Here, I'm trying to point to it right there. There's no way to type it in so you get a squared right after the sign. Instead, you have to type it in like this. So you would have to do sine x and then square it, and then minus 1/2. Another thing is zoom trig is really helpful. I would recommend doing that anytime you're trying to graph a trig function. So you go menu, number 4, and then number 8 for zoom trig. If it asks you to find solutions, that's where it hits the x-axis, or where it would be 0. So you can go menu, analyze, and then find the zeros of the function. What you need to remember is we want our solutions to be from 0 to 2 pi. But if you look at your graph, the x and y axes are not in terms of pi necessarily. So what you have to remember is that 2 pi is about 6.28. So if I'm told to go from 0 to 2 pi, that means I only want to find solutions from 0 to 6.28. So I would be looking for where it hits the x-axis in those spots right there. And again, you would do that menu 6-1 and it'll give you the solutions. Okay. Okay, now this is a slightly more advanced kind of solving, these next few problems. These are called multiple angle equations. The difference being, let me make it a little bit bigger. The thing that's different is now you're going to have this number right here in front of the x. If you go back and look, none of the other examples we've had so far had a number in front of the x. There might have been a number out in front here, but that's different. So these are called multiple angle problems, and whatever that number is in front of the x, that's indicating how many times you're going to go around your unit circle. So in this particular problem, that means we're going to go around the unit circle twice. Okay, so you're going to start solving it just like we did in those other examples. In order for me to get rid of that cosine, I can take the inverse cosine of square root of 3 over 2. Now, this 2x, that is still a 2x. I was not able to divide by 2 right from the beginning because that was stuck inside the cosine function. Now that I have taken the inverse cosine function, eventually I will be able to divide by 2. But I have to find these solutions first. And remember, I got to go 2 times around the unit circle. Okay, so where do we get positive cosine? That happens in the first and fourth quadrant. And we're looking for where we get a square root of 3 over 2 in the cosine spot. Oh, and also I'm told that I'm supposed to solve in degrees. So you get a square root of 3 over 2 in the cosine spot at 30 degrees. And so we would also get it over here at 330 degrees. So I'm just kind of going to list out all the solutions. Now what I need to go is 2 times around. So I already went to 30. I already went to 330. Now I need to go again. So I can add 360 to get my next angle. So that would be 390. And then I can keep going until I get here again. So again, it's adding 360 degrees. It's just like a coterminal angle. So 330 plus 360, oops, that would, let me erase that. That would give us 690. So here's one time around, here's the second time around. All I did was add 360 to 30 and add 360 to 330, and that's how I got these two. Okay, now in the end we need to know what x is. So now is the point where I'm going to divide all of these by 2. so that I get x all by itself. So 30 divided by 2 is 15, 330 divided by 2 is 165, 390 divided by 2 is 195, and 690 divided by 2 is 345. So these are my final answers. And what I want you to notice is that all of them are between 0 and 360. Just like it said up at the top here. So in the very end, that's when your answers should be, between 0 and 360. So again, we had to go twice around because of that 2 right there. We're going to try some more. Okay. For this one, probably what most people would do, just because they're on autopilot, is they would add 1 to both sides. And then this 2 out in front is being multiplied, so we are allowed to divide by 2. And now here's the point where you are going to be tempted to divide by 3, but you can't divide by 3 yet because that 3 is stuck inside the cosine function. What you can do is move the cosine over to the other side by taking the inverse cosine of 1/2. Now that 3 indicates we have to go 3 times around. So I'm going to leave it as a 3x for the moment, and I'm going to solve the inverse cosine of 1/2. So where do we get 1/2 for cosine? That happens up here at pi over 3. Where cosine is positive also in the 4th quadrant. So that would happen down here at 5 pi over 3 as well. So those are my 2 solutions going 1 time around. Pi over 3, 5 pi over 3. Now I need to go a 2nd time around. So I'm going to add 2 pi. Just like in the last problem, I added 360 degrees. Now I'm going to add 2 pi. But remember, you need a common denominator. So really what we're doing is we're adding 6 pi over 3. So if I add 6 pi over 3 to pi over 3, I'm going to get 7 pi over 3. And if I add 6 pi over 3 to 5 pi over 3, I'm going to get 11 pi over 3. And then we're going to do that again. So now add 6 pi over 3 to 7 pi over 3. 7 pi over 3 plus 6 pi over 3. You will get 13 pi over 3. And then do the same thing with 11 pi over 3 plus 6 pi over 3. You'll get 17 pi over 3. Okay, now, in the very end, we have to get x alone. So that means we are going to have to divide all of these by 3. Okay, now just a little side work, just to be careful. If you have pi over 3 divided by 3, that would be the same thing as pi over 3 times the reciprocal, which would be 1/3. And when you multiply those together, you get pi over 9. So when we're dividing all of these by 3, the denominators are all going to be 9s now. So I'll have pi over 9, 5 pi over 9, 7 pi over 9, 11 pi over 9, 13 pi over 9, and 17 pi over 9. And those are all of my solutions, and they all fall in the interval 0 to 2 pi. You're going to have way more solutions for these multiple angle problems. We're getting close to being done. This one is an important one to try because when you first look at it, you notice that you've got sines and cosines, and that's kind of gross. So we would want to get all of the trig functions to be the same. So you're going to have to use your knowledge of identities and try to be a little clever. So for example, sine squared x, that comes from the Pythagorean identity, sine squared x plus cosine squared x equals 1. So if I just wanted the sine squared x all by itself, I could subtract the cosine squared x. So wherever I see a sine squared x, I can replace it with a 1 minus cosine squared x. The rest of this problem will stay the same. Okay, so now at least all of our trig functions are cosines now. So now what I would do is distribute that 2 through. So we're going to have 2 minus 2 cosine squared x plus 3 cosine x minus 3 equals 0. I've got like terms that I can combine. So I will have negative 2 cosine squared x plus 3 cosine x minus 1 equals 0. And this to me looks like a quadratic because I've got a trig function squared, I have a regular trig function, and I have a constant. So I'm going to treat this like a quadratic, and I'm going to factor it. But I don't like factoring with a negative leading coefficient, so what I'm going to do is just switch all of the signs. So I'm going to make this a positive 2 cosine squared x, I'll make this a negative 3 cosine x, and then this will be a plus 1. Okay, so now we're going to factor. So 2 cosine squared x, that means that one of them has to be a 2 cosine x and the other has to be a cosine x. In order to multiply to 1, both of these are going to have to be 1s, and the tip-off is this middle term is negative, so those are going to both be negatives, because a negative 1 times a negative 1 is a positive 1. But you can just double check, you know, like the outsides would be a negative 2 cosine, and the insides would be a negative 1 cosine, and that makes the negative 3 cosine. Okay, now that you got it factored, you set each factor equal to 0 and solve. Okay, so I would add 1, and I would be allowed to divide by 2 since it's out in front. So cosine of x equals 1/2, and then I will take the inverse cosine of 1/2, and then I will think, okay, what angles do I get a 1/2 in the cosine spot? Okay, so that is going to happen at pi over 3 and at 5 pi over 3. Excuse me. And then over here we're going to add 1. And then I will do the inverse cosine of 1. And where do we get a 1 in the cosine spot? That happens right there at 0. So those are our 3 solutions. I'm going to skip that one just because of time. And then these will be the last ones right here. Okay, now we've done this kind of problem before, so it should feel like review. But we're solving, so that's kind of the new added level. So here, I can divide by 5. So sine x would equal 3/5. Now, when I go to do the inverse sine of 3/5, 3/5 is not on your unit circle. So this is where we need to use our calculator. If you type in inverse sine of 3/5, you're going to get 36.87 degrees. I'm sorry, I'm coughing so much. And that is where sine is positive, because 3/5 is positive. So the other angle we need to find is over here, because that's also where sine is positive. So if going that way is 36.87, then this should also be 36.87. So I could do 180 minus 36.87, and I will get 143.13. All right, last problem. Subtract 2. Divide by 3. Then do the inverse cosine. Again, you got to use your calculator, because negative 2/3 is not on the unit circle. When you get your calculator, it's going to be 131.81. And this is a negative value for cosine, so that's going to happen in the second and the third quadrants. So 131 is the first angle we got, so we need to find this angle right here. Well, if you went 131.81 that way, you could go 131.81 the other way. So you could do 360 minus 131.81, and you would get 228.19. So that's the other angle. Okay, so that is it for 5.3. And now you will have some time to work on homework.